Hi class, so in this video we are going to enter the new chapter, which is your internal combustion engine. So in short, we name it as IC engine. Okay, so you have a look at your notes here. You are going to learn about this Otto cycle, and this we are going to use the PV diagram, right? Because our concern is on this volume, the compression and then the expansion. And then afterwards, we are going to have a look at this diesel cycle. And finally, and also diesel cycle is going to use your PV diagram as well. And finally, we are going to have this dual combustion cycle, right? Dual combustion is actually a combination of your Otto cycle and also your diesel cycle. Alright, before we continue, there are several things that you need to bear in mind, right? So in this internal combustion engine or your IC engine, you are going to analyze it in a closed system where you have this piston cylinder, and the things that you are going to analyze is inside this closed volume, right? Closed system. So you are going to have top dead center, where in here where your piston stop, right? When compression happen, the piston stop at your top dead center, and the bottom dead center is when your piston expand or retract. So where does your piston stop? There will be the state of your bottom dead center, right? And this expansion and compression, compression and expansion, we mix we name it as a stroke. Okay. Next, you need to bear in mind that the concern of internal combustion engine is how much your heat produced from the combustion process, and then to get your work net, how much power being produced. So you need your Q out here, right? And the things that you need to also bear in mind is about your compression ratio, and then you have another term in diesel engine, which is cut-off ratio, and as well you have this mean effective pressure. Okay, so we start first with your Otto cycle, where the heat addition is at constant volume. So how does this process happen in visual? How are you going to visualize this process happen? So let's have a look at this YouTube video. Alright, so you go to your YouTube channel where you type this gasoline engine, so it's going to appear this thing, right? So this is the anatomy of your piston cylinder. Okay, we stop there. So this is where your bottom dead center, where when the piston expands, so it's going to stop at here. So we name it as your bottom dead center. Okay, if you have a look at your notes here, so this will be your bottom dead center. And how in your PV diagram, your bottom dead center will be the maximum volume, right? Okay, next, the top dead center is this one, where your compression stop. So this is your top dead center. So you can see from your PV diagram, your top dead center is here. So when the piston cylinder compress and it stop at your top dead center, so this is your minimum volume. Okay. Alright, because this is a gasoline engine or petrol, or also known as Otto cycle, right? So you're going to have a fuel injector here, and your air uh, will be flow in from the outside into your piston cylinder through this fin, right? So once it's injected, it's going to be the fuel is going to be vaporized and mixed with your air, and then it's going to be sucked into your piston cylinder here. So let's have a look at this video. So first we have this intake stroke. So you see the moment the air is come in, so your camshaft is going to rotate this thing and push this valve open. So you are going to have a mixture of fuel and air together into your piston cylinder here. So together with this is where the plot of your PV diagram. This is actually at this phase, right? You start with this intake stroke at 1, where you have a maximum volume here, okay, and that this is where your air and fuel is being mixed up. All right. Now, this is where the compression strokes happen, right? So this is your bottom dead center volume. So now it's going to compress upwards. So this is where your plot right now from this bottom dead center is going to compress up to your top dead center over here. Okay. And then next, what is happening? So it's going to, it's going to have a spark here and burns the mixture. Once the mixture is burned, if you have a look at here, this is at constant volume phase, yeah. So this is why your combustion is happening at constant volume. Okay, your piston is fixed, stop at here, it fixed right here. Okay, while the process of combustion is happening. That's why you have Q in, where combustion process is happening at constant volume. So let's watch this one. Right, so once your fuel and air is going to explode and the burning is happening, now it will expand, right? This is your fuel and air is already fully combusted, so now it's going to expand here. Okay, and finally is this exhaust process. So you can see that the exhaust process is happening also at constant volume, right? Where at this bottom dead center, your valve here is open, so you reject this product of your combustion. So this is what makes one complete cycle. So therefore, when analyzing your Otto cycle, right, your Otto cycle, you are going to have state 1, where the compression starts to happen, state 2, where the combustion is about to happen, state 3 is the final of combustion, right, and then you are going to expand this piston cylinder, and then finally heat rejection. So 1 to 2, we call it as isentropic compression. 2 to 3, we name it as constant volume heat addition, because the volumes stick at that top dead center. And then you are going to have isentropic expansion, and finally your constant volume heat rejection. So you are going to use the isentropic for ideal gas equation. So this is the isentropic ideal gas equation, where when you have an isentropic process, you are going to make use of this. It's the same with your previous thought in Brayton cycle, but the constant in Brayton cycle is between your temperature and pressure. But for this closed system in internal combustion engine, your constant is your volume. Therefore, if you have a look at here, you are going to have compression ratio, which is between V1 over V2, or if you take a look at your PV diagram, right, V1 over V2 is actually your V maximum over your V minimum, or your bottom dead center volume over your top dead center volume, and this is what makes as your compression ratio, right? So we make use of this compression ratio into this isentropic process, so that we will get the property that we are going to need, right? Of course, at the end of the day, what we are concerned is to find your thermal cycle efficiency inside this piston cylinder. Alright, so it's going to be the same. You need to find your work net, where your work net can be found from Q in minus Q out over your Q in. And this is ideal gas, so your concern is on the temperature. And because of this is we are analyzing our closed system, so we are going to have use your specific heat at constant volume. Okay, so in next video I'm going to show you about diesel cycle. Stay with me.